So our next speaker needs no introduction for anyone who's read a paper in zero knowledge proofs. He's none other than Giacomo Fenzi. He's a researcher from EPFL, and today he is going to present STIR, which is an improvement over Fry, and we're really excited to have him here. So give him a huge round of applause.
Thank you for the very kind words. Now this works. Perfect. Yes, so today I'm going to be talking about STIR, which is read-column proximity testing with fewer queries. This is joint work with my advisor, Alessandro Chiesa, Galarnon, and IOPP. And so we're going to be talking a bit like the high-level view of why you should care about this result. So and how now it's in blockchain, and then we're going to go for a technical deep dive. And then if I have some time, I can give some intuition and some exciting recent work to follow up from this. So let's start with some motivation. And now one of the many uses for them, apart from the ZK login, is to use them for scalability. So in general, you want blockchain as an obvious scalability problem. You have a certain throughput that you can only achieve. So there are the number of blocks that can be like minus a certain amount of time, and there's only so many transactions to put in a block. And this puts a limit on how much things you can actually do per in the number of transactions per second. So one natural idea is to try to scale this up and to try to give more for each transaction. So you have your blockchain, and now you want to scale it by using a rollup. And rollup the way they will work is that instead of submitting transactions directly to the blockchain, they will interact with each other and they will submit transactions to a service operator. The service operator will then update the state. And now you want they will update the state and generate a short proof that the new state that they've updated is correct according to the transaction that they talked about. This proof, which will be short and succinct, will then be posted on the blockchain, and then validators only need to check this proof. And by the essence NARC stands for succinctness, this validation will be in fact much cheaper than actually going ahead and executing the state update function. So this lightens the load on validators and allow you to put more things in each transaction, so artificially scaling throughput. Okay, now that I've kind of motivated why you should care about SNARK, let's see what a SNARK is. So a SNARK is a succinct and interactive argument of knowledge. And in general, we will want to show knowledge of some witness satisfying a relation. So think, for example, the relation of SHA-free pre-images, for example. So this is a protocol between two parties, a prover and a verifier. The verifier will have access to an instance, while the prover will have access to a witness for the relation. And the mode of interaction is that the prover will send a single short proof to the verifier. So the verifier will then output a bit indicating the validity of its beliefs, and this will say whether it believes that the instance is actually in the relation. So this was not a complete picture, because in reality you actually really need a random oracle, unless you do some funny stuff. And this kind of construction can be based on many computational assumptions. It can be based on lattices, it can be based on discrete logarithm. But in our particular case, I'm going to just limit myself to considering it like SNARK, which are constructed in the pure random oracle model. So all that I have is a random oracle. I don't believe any of the fancy algebraic assumptions. I just have a random oracle. And for the purpose of this talk, I will call any SNARK, which is secure in the pure random oracle model, as a STARK. And if you want to debate with me, find me later on or offer me a coffee. They cost here for some people. Okay. Why do we care about pure random oracle SNARKs? Intuitively, you would say that adding more assumption, adding more algebra will give you faster and better protocols. So why would I purposely restrict myself to just use a random oracle? And the reason is that when you have a pure ROM SNARK, the heuristic instantiation gives the SNARK which have amazing features in practice. So first of all, they can have a transparent setup, so they can be, you don't need to have a trusted setup which is dependent maybe on the circle, like a Groth 16 proof would have, or that's dependent on the circuit size, like a KZG one would have. You can actually, the only thing that you need to figure out is which hash to use, which is already quite nice. Then, since you don't have algebraic structure, you don't need to use any expensive public key cryptographic operations. So for example, you don't need to actually work over a 256-bit field for like elliptical operation. You have a lot of freedom in which kind of field you want to work with. And finally, the arguments in the ROM constructed in a way that we'll tell you next are post-quantum secure in the quantum random oracle model, so the resulting heuristic instantiation is plausibly post-quantum secure, which is also something that is a nice to have. So all these characteristics led like Stark to be used widely in practice to secure now billions of dollars real-world blockchain. And here I've just put a bunch of different logos of people that use the Starks in practice. Okay, so how do we end up constructing the Starks? And the way that the paradigm that has been successful in this is something which is called the BCS transformation. So this is a combination of two tools, an information theoretical proof system and cryptography. So the information theoretical building block that we're going to be using is what's called an IOP, an interactive oracle proof. And this is a protocol between a prover and a verifier, which makes sense. We're trying to build a Stark at the end of the day. And the way in which these prover and verifier interact is that the prover sends you messages, which are oracles. I'll explain what this means later. The verifier will answer with some randomness, and this interaction will go on for some rounds. Now, these are oracles, so what does it mean? Well, the verifier does not have to read this oracle in their entirety. It can just ask to read some bits of it. So for example, you can go and look at these locations. And the crucial point is that in this model, the prover is not able to change what is sent once you've sent it. Once it is sent, it's done, and the verifier can go and read it. So, more things. Okay, once I have one of these IOPs, I can convert them efficiently into a Stark by doing the BCS transformation, and this gives you a Stark. So basically the idea is that to emulate the oracles, instead of like having oracles which don't exist in the real world, you Merkle commit to the proof string. And then when the verifier wants to query those points, you verify the Merkle path. So why would you want to do this? Well, there are two features that we kind of like care in the IOP, which are the proof length and number of queries. Proof length is the total size of oracles sent, while the proof queries is how many locations are being queried. And in practice, you can think that the proof length is large. It's usually the size of the circuit. So think 2 to the 24. The number of queries is small, so like around like say 400 queries, give or take. When you compile, your argument size depends linearly on the number of queries and logarithmically on like on the proof length. So now by compiling, you basically, if your number of queries was small, you get subsameness. So you don't have and then nothing which we only depend logarithmically in the size of the circuit. And in this talk, we're going to be focusing on constructing this building block, IOPs. Now, how do we construct IOPs? Well, we're going to compile them from something more, so I have another compiler in here. So we're going to take another tool, which are called polynomial interactive oracle proofs. These, what are they? Well, you've seen an IOP, they're exactly the same thing, only that now we further constrain the prover to only send you polynomials. So again, they interact and will send oracles, and the prover, and now the verifier can now query the polynomials anywhere in the field. Okay, so, but the prover can only really send the whole polynomial. So imagine you send the coefficient, and when I query it, I just evaluate it. Now, what I can do is I can use things which are called Rich-Solomon codes to do a redundant encoding of these polynomials. And then use the main subject of this talk, proximity testing, to check the claims that we will induce. So, in particular, what we will do. Okay, so we suppose that we have a starting polynomial IOP, which is good because there's a bunch of them you can use. You can use Aurora, you can use a Stark polynomial IOP, and then we're going to be using it to construct an IOP. So, what will happen is that we will run the prover of the polynomial IOP, which will give you some polynomial. That's what it says on the can. And then, instead of sending that, we will send an encoding of it. So imagine that this is like the polynomial with some redundancy, which enables us to efficiently check things. Then we will run the verifier of the polynomial IOP, which will then send you some randomness, and then at some point, you might want to query f at some point z. okay, cool, now I want to see this f is a redundant encoding of it, and I want to check that the thing which is behind the encoding, this p, actually has some value. So what I will do, I will ask the prover to send me what the value should be, and then since I cannot trust the prover, I'm going to check this. And the way I check it is by testing one quotient. So we'll explain a bit more what it is, but this is roughly the way that you can compile it. So the redundancy enables you to check constraint on the encoded polynomial via this proximity test, which will say exactly what they mean. And what I want to hammer on is that, like, when you do this kind of compilation step, around 80% of the resulting argument size after BCS and all of that, even more than that, I was conservative with this 80%, just come from the proximity test. So the queries of the proximity test are really all that contributes to the argument size. So by improving this building block, we can really improve the efficiency of the resulting argument as much as possible. Okay, so what is this tool? So first of all, let's see what our rich Solomon code is. So this is what going to be the main object of our talk. So we parameterize it by 3 parameters. So okay, in this talk, I'm going to assume there's a field. We need some conditionality field. We'll talk to me later if you're interested in which exactly you want, but they're reasonable. So the 3 things are n, d, and rho. So n is the size of the evaluation domain, d is the degree of polynomial, and rho is the rate of the code, which will be the very important metric for us. So what is a rich Solomon code? Well, the way that I do this redundant encoding, I take my polynomial, which will be of degree d, and then I write down all of this evaluation on this domain L of size n. For completeness, think that d is maybe 2 to the 20, n is maybe 2 or 4 times bigger than that. So now I have something which is more than enough information to recover the polynomial, but a lot of more. And the rate is kind of the measure of how much redundancy you have. So if the rate goes down, you have more redundancy. So if the rate is 1/16, that means that n is 16 times bigger than d. So that means there's a lot more redundancy. And we will see how this redundancy gives you a trade-off on how easy the code is to test. Okay, so question on rich Solomon codes. I mean, these are beautiful, amazing, they're used everywhere. Yeah, I think, yeah, they're incredible. Yeah, so this rho is the rate of the code, and this is what we'll be focusing mostly on this in this talk. What's an IOP of proximity? Well, an IOP of proximity is just like an IOP. So you have a prover and a verifier. And they also interact like in IOP. So they send each other oracles, then people can, the verifier can query them at this oracle. But now you have this function f, which is not given to the verifier as an input, but is also given as an oracle. The kind of like property you want to have is that if what the prover has sent is indeed a rich Solomon code word, the verifier will accept it. But instead is that if the function is far from the rich Solomon code word, the notion that we're considering here of distance is Hamming distance, then the verifier will accept with small probability, say to the minus lambda. And the reason why we only give like this kind of like partial guarantee is because we want to minimize the query that the verifier does to both these proof oracles, but also the input. So the verifier is not able to actually read all of the input. And this is where the efficiency of like these IOPs come from. Since I cannot read all of the input, I have no hope of being able to actually check whether f is actually a rich Solomon code word. So all that I can really give is like some proximity guarantee. Also note that kind of like soundness notion that we're looking for here is a round-by-round soundness, which is required because otherwise the resulting argument at the top will not be secure after Feshman. If you know what that means, that's good, otherwise don't worry about it. Good. Let's talk about what our results are. So we present stir, which is, a rich Solomon proximity test. So it goes exactly to fill that box that I was talking about before, which has the following property. So the number of rounds is logarithmic in the degree of the polynomial that you're checking. The proof length is linear in the size of the evaluation domain. And further, the query complexity is this binary expression, which I will explain now by comparing to the previous state of the art. So, the previous state of the art was Fry, and roughly the query complexity of Fry was something like security parameter time log d. In our case, the query complexity is something like security parameter times log d plus log d. Why is this important? Well, the security parameter is much larger than log d. So think that log d is between 20 and 30 in practice, while the security parameter will be 100 or 128. So actually getting an improvement in like the dependency on the security parameter is what actually gives you a lot of concrete practical improvements. Think of this rate as 1/2. This is just a constant, it doesn't really matter too much. But if you squint at this and you ignore this part here, which anyway is not significant, what we have is an exponential increase, an exponential decrease in the number of queries compared to Fry in the part that matters, the one that is like multiplied by the security parameter. So this is where we get our saves. And if you know about conjecture about capacity bounded with Solomon code, everywhere you see a square root of rho in the talk, this can be replaced by a rho. If you don't, these are the provable bounds. Okay. So we've implemented this thing. We have an open source implementation available. Uses our course as a backend over like a 192-bit field. We have both a Fry and a Stir implementation, just to give a fair comparison. It's modular over choice of many things, and I claim for academia is kind of well written. For industry, it probably doesn't make the cut, but for academia, I think I did a decent job. So I hope you enjoy it. And now now we can like look at comparison to Fry. So first of all, I want to stress that wherever you use Fry, you can use Stir. Almost everywhere there's some data availability stuff in which you don't, but almost everywhere you use Fry as an IOPP of proximity, you can use Stir. So this should be a relatively painless change. So we saw that we have fewer queries. So what is the concrete practical impact of this? Well, fewer queries lead to two things. One of them is fewer authentication paths. So this leads to smaller arguments because basically all of the argument size is made of Merkle authentication paths. Next, if you have less authentication path, you also have less stuff to verify. So the verifier has a smaller hash complexity, which means it is faster and more recursion friendly, because now if you have a recursive circuit, you have a lot less hashes to verify. The prover runtime between Fry and Stir is roughly the same. Stir is slightly more, but like maybe a factor of 1.1, 1.2. And the improvements that we have are bigger when the initial degree and rate increase. So I know you might want to see some numbers, so I'm here with the number slide. So these are results for 128-bit security level, 160 bits of protocol security, 28 bits of proof of work, and we use the capacity assumption. So for degree 224 and rate 1/4, Fry has proof of size around 180 kilobytes, Stir is more around 110 kilobytes. While the number of hashes in Fry is around 3.5K, while in Stir we have 1.8K. So we have a 2x reduction in the number of hashes for the verifier. If we increase the rate, so rate degree to the 30 and rate 1/2, this took me a big machine to do. The size was 500 kilobytes for Fry, so almost half a meg, while Stir can get proof of 200 kilobytes. The number of hashes drops from 10K to 3.8K, so almost a 3x decrease in the number of hashes that the verifier needs to do. So here are some more graphs. You can see that basically for argument size and hash complexity, we are better than Fry on every parameter. For prover time, Stir is slightly worse, but not much worse. And for verifier time, there's a trade-off. Around 2 to the 24, the verifier becomes faster. And the reason that this happens is because at one point the reduced algebraic complexity is better than the increased algebraic complexity. And we can talk about this a bit more later. Okay, question about the results? Yes.
The proof of work is only on the prover.
Yes.
Not the verifier.
No, the verifier just needs to verify the proof of work. Yes. Yeah. Exactly. Cool. So let's see, we can go on the techniques. So let me start with a review of the main tool in all of these tests, which is Ritz-Solomon unfolding. So we are computer scientists, we like reduction. So we want to reduce the problem of testing proximity to a Ritz-Solomon code to testing proximity of a smaller Ritz-Solomon code. And you think of one where all the factors are decreased by a factor of k. How do we do it? So not in particular, the rate in this folding will not change. This is a little foreshadowing for later. So now I have some kind of like function f, and I want to make it, I want to test some claim about a smaller function f. What I can do is that I can ask the prover, the verifier, to send me some randomness, and then compute a virtual function, which is called will be default. And what does it mean to be a virtual function? Well, it means that the prover doesn't really need to send me this thing. I can give an access to f, and knowing alpha, I can compute this by myself. How do you do this? Well, you can take an inspiration from FFT. This is roughly the Frey folding. So you can think of taking f, splitting in its odd and even part, and then taking a random combination of the two parts. And this can be extended to like larger arrays of this. Why is this helpful? Well, we have two properties. One of them, there's a property of locality. As I said, if I have access to f, I can query the fold at each point in this domain by myself. I don't need the prover to help me. Secondly, I have a distance preservation property. So these are the entries, these black entries represent the corruption, so the parts in which like the original function was far from Rich Solomon code. And you could think that when I do like this kind of like randomness, things cancel out. What is shown is that with high probability, this does not happen. So the kind of proportion of black corrupted strings are the same between the initial one and the fold. So the fraction of corrupted entities does not decrease. This is a very non-trivial result. This comes from the proximity gap paper, but we're going to use it as a black box. With this thing, let's just talk about what Frey is. And Frey basically is just applying this and doing some consistency checks. So ideally, I could keep folding until the end and just check that. The issue is that if I do that naively, the number of queries kind of like grows exponentially. So I need some way to break this recursion. So what I will do, I'll first fold, and then I'll ask the prover to send me some new function f prime, which is claimed to be the same polynomial as the fold. Of course, I don't really trust the prover because it's a prover. I cannot trust it by definition. So I have to kind of keep him accountable. So I check that the fold and this f prime are actually the same. And then I just keep recursing on this f prime. So this is basically Frey. It's not really Frey because in the full Frey you actually do correlated checks. But I think this pedagogically is more interesting. So soundness is kind of like easy to show in this case, much easier than the full Frey analysis. So if the new function is a Rich Solomon code word, then fold will be far from the original one by these proximity gaps. And then it must be, in particular, it must be distant from f prime. And so if I check it at a few random points, I will end up like that my soundness error is roughly 1 minus the distance to the t. Sorry. So in particular, if I want to get the soundness error I was talking about, roughly I need to set my t to be the same in each round, and that to be like lambda divided by minus log square root of rho. So if I do this for log d round, I essentially get the query complexity of Frey that I gave you before. So roughly you get like log d times lambda divided minus log square root of rho. So let's see now how we can like improve this. And so we're going to be talking about the stir iteration. So the stir is going to be exactly the same. You're going to compute a fold. But now I'm going to ask the prover to send me a function g, which is not, as you can see, like it's larger than fold. So it's not as in Frey, which is the same thing. So they're going to still be claimed to be the same polynomial, but they will be on two different domains now. So in particular, g will be a domain of size n over 2 and not n over k. So roughly, my domain has become greater. I have more redundancy. So the intuition that you should have is that more redundancy makes things easier to check. So I'm trying to improve the redundancy to then reduce the amount of work I have to do to check things. So now I cannot really check these at the same point because they're not, they might have even no intersection, these two things. So I need to have a new protocol to like do things, and this is the domain shift protocol that is the real innovation of stir. And this will be some protocol which makes t queries to the original function, and then it spits out a new virtual function f prime. And we can like now recurse on this f prime by now checking at a different code. So you see that, this is actually supposed to be n over 2, sorry. this will be a different code in which like the degree has gone down by a factor of k, but the domain size only by a factor of 2. And now my rate has improved. So yeah, this is a smaller rate. And now, like the property of the domain shifting is that roughly, if the fold is far from the Reed-Solomon code, then this new function will be far from this new code, unless it has more probability. And in particular, we both get a larger distance and a smaller rate. What does it mean practically? Well, that if you could do the recursion, the rate keeps going down. The rate becomes like 2 divided by k to the I times the original rate. So I can now set like my TIs to depend on the rate for that iteration. And this means that you have fewer queries each round. So in particular, for an example, you can see the rate goes from 1/2 to 1/16, 1/28, and the queries start from 200, 50, 29. While in Fry, for example, there will be 200 at each round. So this is where you get the saving. Already, like in the second round, you have a factor of 4 saving with Fry, and then you just keep getting more and more savings. And this is what leads to the efficiency of stir. Okay, so talking about what the domain shifting, I don't know how much time I have. Yeah? Okay, so domain shifting is basically using some of the ideas that we've seen before. So roughly, you want to check the two things that are claimed to be evaluation of the same polynomial, and you want to define a new function. So the way that you end up doing this is that, I'm going to skip that part quickly, you end up testing a function which is a quotient. And quotient, as we've seen before, kind of enable you to test consistency. So there's a claim from the paper which is not too hard to show that says that if the closed polynomials do not have the consistency, this f prime will be very far. And this can be amplified. I'm going to skip the auto domain protocol because I don't have time. But roughly then, stir is just a combination of these protocols. So you have a folding step, an auto domain sample, which is the same one with Fry and Dipali, and then a domain shift protocol, and then testing some quotients. And then you just keep recursing this. So just to conclude, we present the stir, a new interactive oracle proof of proximity for its Solomon codes, with better asymptotic query complexity than anything that was known before. There are some things that we didn't cover, like our compiler. And I want to just spend one moment about talking about some exciting follow-ups that we have coming through. So we saw before that there was like an open question about the verifier complexity. We managed to help it, and there's our new work, which is WER, which means weights help improving rate. So we have new techniques which significantly help the verifier time and give now a multi-linear PCS, which is more than what stir could do, because stir could only do univariate stuff. So the verifier time is much, much better. So you can see this, the red line is Fry, the blue one is stir, and the green line is WER, which is, you can see is there's a bit of a gap between the two things. In fact, so this is now the smallest, WER has got the smallest proof in the pure random oracle model. And furthermore, the verifier is so good that it gives you the fastest verifier of any polynomial commitment scheme, including those relying on pairing, including those relying on trust, etc., by a factor of around 4x. So this will be soon on ePrint, so I'm happy to give you this sneak peek, and I hope this leads to like more Stark-based construction being deployed in the wild. So I'm happy to take any questions. I don't have time for that.
Thank you very much, Giacomo. Maybe we have time for one quick question before we move on to the next talk. Otherwise, are you still around for the day?
I'll be here today and probably after tomorrow.
Okay, amazing. So if you have any questions, I'm sure Giacomo is happy to answer them. I'm also going to approach you later myself. And also, thank you for the sneak peek. Yeah, big round of applause again.